Please come in, have a seat. We're ready to start with the afternoon session. This afternoon we have the IGF editor keynote. This is why I'm hosting it. It's very nice to have you here again. We have a 1 hour time slot for this keynote with a presentation and some time for questions. But before we get started, I have to remind you to always check WOVA, the app. There's been a few changes with schedules, especially Wednesday afternoon with the closing keynote and the parallel session. They have been swapped. So please make sure you update your agenda. And there may always be some small changes. So please just make sure you always check the agenda there. It's up to date as much as possible in near real time. So it's my pleasure this afternoon to welcome Yan Liu, Professor Yan Liu. She's a professor in the Computer Science Department and the director of the Machine Learning Center at the University of Southern California. She received a PhD degree from Carnegie Mellon University. Her research interests are within machine learning for time series and its application to climate science, healthcare, and sustainability. She has received several awards, including NSF Career Awards, a Kawa Foundation Research Award, New Voices of Academies of Science, Engineering and Medicine, Best Paper Award in SIAM Data Mining Conference. She serves as General Chair for KDD 2020 and ICLEAR 2023, and Program Chair for WSDM 2018, SDM 2020, KDD 22, and ICLEAR 2022. It's our pleasure to have you here, Yan Liu. The floor is yours.
Thank you. Thanks a lot to Pierre for the kind introduction. I also like to thank the organizers of this conference for inviting me. It's really a great honor to talk, to share my adventure in time series in the audience of forecasting experts. So my whole career is focused on time series. I really want to share why I was really intrigued by time series. So the universe we live in starts as an orderless singularity. Then we have the Big Bang, which marks the birth of time and space. It's also a moment that marks the birth of patterns, causalities, and many the patterns that we're looking for in the universe. So human, as we started, we are always interested in finding out the principles of the universe and trying to identify patterns, making forecasts. A lot of the time before we have industry revolution, this was mostly done by analyzing data from very few snapshots. For example, in ancient China, we basically record the climate mostly on these paper records, and then the peasants looking for patterns and predicting what will happen for the next season so that they can plan for farming and harvesting. And then for Darwin, what he did is that just observing all these different types of finches and the shape of this finch, and then basically inferred from these snapshots of data in terms of the evolution theory. Obviously, with the satellite imaging technologies and sensing technology, we are developing really fast. And now we are able to get access to large amount of data. For example, in climate domain, we get access to petabytes of data where we will be able to make accurate forecasting of weathers, extreme weather and climate patterns, and also planning for what we want to take actions in the event of extreme climate. Similarly, in healthcare application, we also see a big birth of time series observations of the human body, where we will be able to have smart patient monitoring as well as for the mobile health for monitoring the human activities so that we will be able to help patients with long-term disease. Similarly, in transportation, where I spent my sabbatical years in 2018 in Didi, that's a Chinese Uber, where we're developing all these modern technologies to making accurate forecasting for the traffic system and also making predictions on the ride share demand and etc. Last but not least, then the creation of the web, where we basically have many different type of time series. For example, we can have the web traffic monitoring and forecasting. Now in e-commerce, we'll be able to predicting the sales, and similarly in social network, we'll be able to analyzing the time series of activities on social media to predict whether there will be an outburst of hot topics and etc. So by now that you have hopefully been very convinced that now we are in this big wealth of time series data, and all the major companies is trying to utilizing this vast sea of time series so that we have already achieved some great success. For example, here we have the GraphCast and also the Pangu weather prediction. So last year I went to a conference specifically for weather forecasting and climate forecasting. Everyone there as an expert in climate and weather system are using GraphCast or Pangu system. And similarly, now that we have the supply chain management and then the transportation system have all been revolutionized by this. So now I want to go back to the fundamental question, because when we try to develop model, we need to understand what is the essence of time series. Hopefully more standardized in the large language model architecture. Basically that we're going to have this transformer blocks. We're also going to have the LORAC, that is low rank adaptation, so that we can quickly have the efficient distribution adaptation. And then afterwards, we're going to have this component-wise output combination so that we'll be able to predict the trend seasonality and also the residue so that we can combine them into the final prediction for the target domain. And that is basically the architecture for the tempo model. So next we want to quickly show the experiment results where we study for zero-shot cases, basically that we do not have access to the training data in the target domain. And then we're going to train the model, the tempo model, using these diverse sets, for example, the weather, the electricity, and many others. And then, for example, in here we show that the results for zero-shot prediction comparing with predicting for electricity, traffic, and etc. So here we show the numbers in terms of MAE in 96 horizon and 192 horizon. So tempo is represented by the blue bar, where we can see that the lower the better the value, and therefore tempo were able to outperform the state-of-art methods in these zero-shot cases. So next, I also want to quickly show and compare the results between the zero-shot tempo compared with a full-shot learning model for the state-of-art methods. So full-shot means that these models that we're comparing with will have access to the full training data. For example, in this energy data set, the ETTH1 and ETH2, the model, for example, here we show the patch DST, iTransformer, and etc., where that they will be training on these data sets in domain. But for our model, tempo model, is doing zero-shot. That is, we do not have access to any of the data in that particular domain. And here, to our surprise and nice finding is that actually the zero-shot tempo will able to achieve similar prediction performance, or sometimes a little bit better than the full-shot state-of-art methods. And this really shows us that there is a promises that we are able to actually do foundation models for time series. And this is very encouraging results at that time. And later, because we have access to the prompt module, therefore we will be able to include the contextual information. So in these data sets that we created, we not only have access to the time series data, but also have different type of data in terms of the news about the company, for example, for the EBITDA value prediction, or the news content itself in the Google trend prediction. And in this model that we can see that utilizing this multi-model tempo, we are able to achieve better results comparing both using the time series model itself, and also other models were able to use both the text and also the time series data. So this also shows that by incorporating this STL decomposition, that is residual trend and seasonality decomposition, and capturing the unified patterns of time series across different domains, give us some really good hope of building this foundation model. So after different type of foundation model of time series have been developed, there's also new development in terms of the data sets. Salesforce provides this pretty much the biggest data set for time series model, and then they create this leaderboard. In there, the data sets is big in the sense that they have 24 different data sets with 177 million data points for us to train. As academia people, we have a difficulty actually training on these big data sets. Obviously, with all the major companies, they have access to the cloud computing services, but for us, it is very difficult. So my students and I have been working on this and trying to find solutions. And then we started to thinking a little bit about the challenge that we're facing in both the large language model for text and also for the foundation model for time series. In the sense that when we're looking at this parameter size and also the inference time that has to be developed and has to be used for training all these large models, is really exploding. For example, even for the smallest model, for example, this GPT-4 TS or Mirai, it still needs to have 86 millions of parameters or 14 millions of parameters. And when we grow the data, it means that we're going to have even more, and we'll be facing exactly the same challenge, is that we're going to be running out of all the memories, the storing and also storage, and also the computing resources needed. And therefore, we need to find a solution. The way that when we're looking at them is that it's not only a computational issue. There's also other issues that known in the large language model community is about catastrophe forgetting. That means that because the model is trained on so many parameters, we basically will forget a lot of important things happened before. And there's also this difficulty of updating the model. ChatGPT has to be updated every a few months because they can't afford the model to update the model really frequently. And therefore, that we really need to find some alternative solutions, especially for time series. And the way that we're looking at this is that we want to go a little bit different path. Instead of training this gigantic model, which is very difficult for academia to do, but also that when we're looking at human natures, we were not created as a super powerful monster with a huge endless memory and trying to learn things. The way that we're built is that nature created us, all the human beings, as all of us. We have many of us. And then each of us working together in order to learn and infer together. And therefore, that maybe we should do something a little bit different. Maybe we should looking at how we can do some ensembling approaches. And here we refer as to wisdom of the crowd. So in here that we're looking at this hierarchical ensembling approaches, which means now that we're going to build many different of smaller models. And we can have many different ways to build smaller model. So here in the specific way that we try to address this Salesforce leaderboard data sets, what we did is that we're looking at 3 different domains, 3 different type of models. So the first one is that we're going to have some general fine-tuning model. I'm going to show in here, basically that we get access to the complete data sets. And then we have some short horizon model, median forecasting horizon, or long horizon model. So this is in terms of building this general purpose, but across different prediction length type of models. The second one is that we're looking some domain-specific expertise. So there are 15 domains in these data sets, and therefore for each particular domain, we're going to have some fine-tuned models. And obviously some of them focusing on short term, some of them focusing on long term, and therefore in the end, we're going to have about 15 different type of models. And then last but not least, we also have finer granularity. Now we're looking at dataset specific models, which means that in each of the model will be built as an expert on the individual unique data sets. And that means that with 90 different data sets, we're going to have 90 different models. So with access to all these models across different skills, we're going to combine them in the end, utilizing this sequential least square quadratic programming optimization. That means that we're going to pre-train all these different type of models. And then whenever we get access to a new data points for forecasting, then we're going to dynamically determine the weights for this ensembling model. And then we will be able to basically quickly adapting to the changes or to the specific domains that people are interested in making forecasting, and then hopefully that we can quickly generalize as well. And now, utilizing this hierarchical ensembling approaches, we are able to quickly adapt so that we'll be able to generalize quickly, but also in terms of the inference, it'll be very fast. We will no longer rely on this really long-term forecasting and inference models that we used to do. And now we just need to learn the weights and then just making the forecasting. So now that we'll be able to basically get access to a very robust model, but also adaptive to getting a really good solution. And the nice property about this ensembling approaches is that they are very good in terms of uncertainty quantification. So in this benchmark, they're not only evaluating on the accuracy, that is the MASE, but also on the CRPS, that is basically quantifying the uncertainty. And now combining these approaches, we're able to get this tempo ensemble model. We're able to get the best results in terms of CRPS, and then the number 4 in the leaderboard. And then obviously after NeurIPS, that there are a few models were submitted because they need to making submissions and showing the leaderboard, and then now I think we're number 7 or something. But in terms of the CRPS, we're still number 2. Okay, so this is our adventure in terms of how we're building this tempo model using the simple idea of STL decomposition, and now we can see really interesting results and doing the ensembling to making the results even more scalable and robust. So next, I want to talk a little bit about what happens when we try to apply these foundation models in the real world, in the wild situation. Because most of the cases when we work on these practical data sets, we know that the data are never really well tabulated data in Excel sheets and forwarded to us. It's always something looking at this in the sense that, we actually have a lot of missing data. We also have a lot of irregularity in the data. A lot of them can be 0, and some of them are noisy data sets. And some of them including additional information sources and etc. So from that perspective, we can see that this data in the wild cases will literally involving different type of granularity and different type of noise, different kind of missingness. So how we can actually addressing these type of challenges for foundation model? So last year that my students and I developed this model that is, we call it as time DIT. We want to build this particular model using this deep generative model. And we also want to focus on multivariate time series because in the real world application, we usually have access to multivariate time series, and also we want to capture these nice structures across these multivariate time series. So from that perspective, we can see that it is really more challenges we have to confront it with. And then at the same time, addressing this missingness and multi-resolution. So we borrow these advances in image data analysis. So whenever you go to these different type of website trying to generate images based on the text input you have, you probably know that they're actually building this based on the DIT model, that is the diffusion transformer architecture. In there, that we were giving them the input of the text, and then they learn this architecture from the semantics embedding using the transformer architecture, and then they will be using the diffusion model to generate the images that we're seeing. And similarly here, that we can do something similar. So what we did is that in this time DIT model, we have also two components. One part, or the main part, is really we have access to these different type of data from healthcare sustainability transportations, and then we're going to have this time series masking unit, which I'm going to talk a little bit in the next slides, which will handle the missing values and matter resolution. And then we're going to have this embedding layer, putting them in the time DIT block so that they can have the final projection. And then in terms of the time DIT block, what we did is that mostly about this diffusion module, where we can have the forward processes so that we can add some noise into the data. We can learn a relatively good distribution according to the variance schedule. And then in the reverse processes, we're going to actually learn a relatively clean, better representation of the distribution of these time series data, utilizing this reverse diffusion processes. So that at the end of the day, we're going to get access to this foundation model, which will be able to not only making forecasting, but also learning the distributions of these time series. So quickly, I want to show what we did for the masking units. Here that we have two different type of masking units. So one of them is about this task, the agnostic units masking. It can be random mask or stride. This is really using these masks so that we will be able to actually reconstruct these values. That means that if they are masked, it means that it's missing, and therefore we want to reconstruct the values. And then the other one is that we have some task-specific masking, for example, block masking or reconstruction. Here that we are able to do some fine-tuning for the specific task. For example, that where we're trying to making forecasting for a block of time series, or that we are trying to do the reconstructing, we'll be able to do so in this step. So next, I just want to quickly show some experiment results in terms of how we're doing in terms of zero-shot learning for probabilistic forecasting. Because now we get access to a generative model to learn the distribution, we'll be able to do probabilistic forecasting, which is measured using the CRPS. So our experiment results shows that our tempo model again, our time DIT model again represented using the blue bar, were able to achieve the lowest CRPS value comparing with the state of art. Even comparing with the tempo model or other type of foundation models that developed at that time. Next, I also want to quickly show the experiment results. That is, whenever we are facing the cases in terms of missing value, and then we are trying to making forecasting. And our model, that is a time DIT, it's showing in the red bar, that is able to giving us lower CRPS score comparing with other alternative using the diffusion model. And then once we have access to the generative model, it's starting to give us really powerful things. It's not only giving us forecasting, but also we'll be able to do synthetic data generation. For example, in here, we want to show some data sets that we generated using this DIT model comparing with other state-of-art methods. Here that we show this PCA visualization of this time series data we generated using the DIT diffusion TS, time gun, and time VAE. So we have the original data, which is shown in the red data points, and we have this generated one is shown in the blue dots. So if the data or if the simulation data or this generative model is working really well, we want them to be mixing the red points and also the blue points together. And time DIT was able to do so really well. Well, for others, as you can see that most of them are not mixing really well, and especially for GAN model, that they exhibit very strange behaviors. So at least that we can see that now the time DIT were also able to give us power in terms of generating synthetic data sets, which is one step towards the simulation, building a powerful simulation model in the longer term. So due to the interest of time, I'm going to skip this particular part, but if you're interested in this part of the work, we're also able to utilizing the physics principles and the PDE equations inside the time DIT model, so that for the data we generated will follow the physics principles. I want to save the time to also looking ahead to say that what we're confronted with in the current era. So we have been starting a long time on focusing on these relatively well-defined tasks, for example, forecasting, anomaly detection, even causal analysis. But we all know that in the typical application scenario, we're confronted mostly with complex tasks. So we summarize all these different types of tasks as follows. Some of them are relatively simple, so we can call them as predictive tasks. And then we can have diagnosis tasks, analytics tasks, and also these more complex decision-making tasks. So all of them are really utilizing this result of the forecasting. But I would say that forecasting is really not the end, which I borrow, one of the quotes from one of my former students, but now a researcher in Google. But I also just want to say that we all know forecasting is really one step in this complex process. And then the other thing is that we also want to streamline a lot of the processes in terms of interacting with the users, because the users need to understand why we're making this particular forecasting value, and they need to do causal analysis, they need to anomaly detection, and all of them right now is mostly through relatively simple approaches and involving many laborious work. So to be making it more concrete, I want to give two examples. For example, here that this is a very standard complex energy prediction task. So the description will be like, hey, I have access to this particular data sets, right, with relatively humidity and many other observation data we have corresponding to the solar power for the past 86 minutes. And then I would like to actually give a forecast for the next 24 minutes. So our goal is really trying to make the most accurate forecasting, but at the same time, I actually also have some constraints I need you to satisfy. So right now, what will happen is that we really need to take a lot of time to focusing on solving these complex tasks for forecasting, and also involving, as I mentioned, interpretation. When the prediction is not really good, we need to understand when it doesn't work really well, and then we need to do anomaly detection, identifying the causes for the wrong prediction. So this is itself is really difficult and laborious. And similarly, that we know that when we try to do this investment strategy generation, that means, for example, here I have the stock values, right? And then I want to make an investment to make at least a 1.31% profit. Please give me, this forecasting, but also give me the investment strategy. So that means that this forecasting is also in a very complex tasks, and it's very difficult and laborious. So this is very much like what we have been doing in the pre-industrial time, where that we have all these workshops, and all of us working as consultant or these workers, in these workshops, and trying to take months to give answers. At the same time, now that we have a new concept that is really fast developing, and many of the AI companies are doing, is the so-called agent system. So that means that we may develop some co-scientists and also the agentic AI system, so that we will be able to democratizing this whole processes of forecasting and many other different type of analytic tasks in one shot. So it is still a long-going work, but I would just like to share some recent progresses that we made. So in this particular work that we made, we just made a submission to, where we develop this agent system that will be able to do this type of task. But before we do that, I want to just reverse back to say that because ChatGPT and other foundation models are so powerful, can we simply just throw all these data and also give us queries and then asking the ChatGPT to figure out everything themselves? So this is what we did. I said, let's first write a prompt to just say, here are the historical values, right, of this time series, and then please making predictions for the next 11 days. And then many of you are experts in forecasting. I'm sure you have tried and pretty much have a really good intuition that the current ChatGPT model or the current ChatGPT model were not able to actually get really good prediction results. As you can see that the values that they are able to make are really far away from the actual prediction. Because they probably don't know the seasonality, and obviously that they just choose to repeat some random stuff in there. And more fundamentally, there are some designing limitations for the large language model. So the first one is because that they lose the continuity and discretization errors. Because whenever we put all these data into ChatGPT, the first thing do is they are going to do tokenization. And then they are going to discretize what we observe as continuous values into something the transformer architecture can capture. And there is the information loss in there. And the second one is that there's also this embedding mismatch. Because most of these large language model they're building is really embedding, learning a very good embedding for words that is a human language that we're speaking, but not necessarily for the time series continuous values. And then when we try to align these two, they may not necessarily align really well. And that's also why that this mismatch embedding creates this issue. Last and not the least, there's also this temporal structures that have been ignored. And this is something that I motivated at the beginning where the structures and the patterns and the causalities are really important, but it is fundamentally lost in this transformer architecture. And that is why that we went through this intermediate approaches where we basically build this hybrid AI solution, which we call as the TS reasoner, that is time series reasoner. They're able to actually capable of doing all these composition reasoning processes by utilizing the development in large language model. But at the same time, they will be able to utilizing the tools that we developed, either as foundation models or simple tasks, even as linear model or other type of models that is our favorite. And then in there, we will be able to actually understanding what type of tasks that we're going to work on in order to answer this complex question. Second is that we can automatically selecting the tools and knowing which tool to call for in order to generating the answers that we want. And then last but not least, there's also going to be a lot of execution and exception handling because the machine is not going to basically working everything all by itself. We all know that there will be a lot of exceptions that we have to handle. So this is the architecture of this hybrid approaches that we develop without going to the details, but basically that there is one central component, which is the time series task decomposer, where that we were given this input of the task description as a text. Then we're going to decompose them into different type of actual tasks and programs that are going to be executed into. And then these programs will be able to call all these different type of operators. For example, this is the time series operator. We're going to have all the tools that we develop for forecasting, causality analysis, anomaly detection, etc. Or we want to incorporate additional information, they will do so automatically. They will be able to pass the input, connecting with the API, getting the data, so that they will be able to return them back. So in this smart system, we'll be able to execute all these different type of tasks automatically to get us the results. And so this slide just basically showing that the way we do this is really by doing this in the numerical operations, so that this is more like automatic programming, like what people are doing right now using the coding. And now we're able to actually program them in a way so that they know what type of operations and tools to get. So next, I just want to quickly show the experiment results before I conclude. Here, for example, when we're looking at the stock prediction and causal relationship prediction, we can see that the TS reasoner comparing with the current state-of-art methods using ChatGPT, DeepSeek, React, and etc., that it consistently get better results. The outer space it is, the better. And especially for the causal analysis, the TS reasoner were able to achieve 87% improvement comparing with the state-of-art large language models. And then quickly, I also want to show the experiments results for the error distribution, where and when there will be exceptions happens. So as you can see, many of them, the ChatGPT or DeepSeek, they have a lot of exceptions in the sense that they were not able to actually execute the commands correctly. And some of them have this inadequate results or constraint violations. Well, for us, that whenever we're able to making forecasting or answering the questions, then we're able to get really good results. So that means that utilizing this more finer grade and also this hybrid approaches, we're able to get better results comparing with utilizing the ChatGPT and foundation models itself. So next, I want to quickly just summarize and to just thinking a lot about what will be the challenges and opportunities for us looking ahead. So I would say the first one is also something Pierre talked about this morning, right? This time series data right now we have access to is still limited in size of and also the diversity. A lot of us working on developing these foundation models is more like a blind person touching the elephant, that we're really touching the corners. In order to see the bigger picture, we need to have access to larger amounts of data and varieties. So some of the work we have been doing, for example, working with the domain experts in transportation, we just released this data sets on these transportation system data sets, one of the largest ones so far. And then working with the domain experts in power systems, we also released this more practical data sets for energy systems in consideration of the time impact to the energy system. So the second challenge I would say is that it's really very fundamental in terms of the model. That is, we really need a balanced model that is capturing both the order and also the chaos. So most of all these models that we developed so far, for example, the transformer architecture, is really for textual information. So that means it's a sequence, it is deterministic. And they are really well that we have been writing this particular easy write for time series forecasting prediction for quite a long time. But now we're really facing this chaotic situation where that now in order to achieve the next advances that we're really on our own. And then there's a lot of discussions right now on social media and also in the community is that whether transformer architecture is really the right model for time series data. It is still hard to say now, but at least we know that we need more powerful models that achieve the balance between the orders and chaos. Last but not least, I think that this point was touched by several talks today so far already, that is causal modeling is really essential for time series. And many of our predictions and forecastings are really impacted so much by exogenous variables. And without explicitly modeling them, it will be making it extremely difficult. So I would just say that in this tsunami of foundation models and large language model, it makes me really nervous every day about what's going to happen in the future. But at the same time, I would say that this is really really exciting moments for us to make a mark in the histories, because this is a really grand time to working on this really exciting topic, and I think that is why they're attracting so many attendees in this particular conference. So with that, I will just conclude and then thank everyone in the audience and also the PhD students and also the postdocs working really hard and the funding agencies. Thank you.
Do we have some questions?
About using the LLM to do the forecasting, and I have read some kind of research. Have read two kinds of research using the large language model. I would like to your comments on this. One of them is treat the time series as the graph, as a figure, as a chart. Input the large language model and ask for the next time step. And another approach is that they explain the time series. Maybe it's drop deeply. That means change the time series into language. Explain how the dynamic in language, and then process the language and make out the forecasting with language, and then transform that into numbers. So I would like to your comments about these two approach, maybe comparing with your approach.
Thank you. Thanks for the question. I think there's a lot of efforts and interest in the community trying to utilizing time series, utilizing the large language model for time series data. And I think that people get some really interesting observations, and you've seen papers to say, oh, that utilizing tokenization approaches were able to achieve the state-of-art results, or simply putting them as a visualization of the time series were able to get really good results. I think whenever we talk about the results, we really have to looking at the problem and the data set that we are working on. So far, a lot of the data that we public available that we call as a benchmarking data sets basically falls into two categories. The first category is that it is a relatively simple task. Near-term forecasting really well-behaved patterns, and therefore even linear model can work really well. And that is why that you see papers to say that, oh, our linear model works really well. Or our LLM-based approaches work really well. Because that is a relatively simple task. Another one is that it is so difficult is longer-term forecasting. The patterns are chaotic, and therefore that it's very difficult for everybody. And therefore that you are really comparing somebody is very, some model that is very, very bad versus another model that is a little bit better, but also very, very bad. So I think that the chaos that we're seeing right now, a lot of them are actually created by the data set that we're using. So one of the data sets that I currently use a lot, really thanks to this community, is the M5 data set, which I think is a really good representation in terms of the patterns of the time series and also in terms of the difficulties, because there are different levels of prediction. And then some levels are easier forecasting, some levels are more difficult. And then you can see the varied capability of different type of model. So I would say that, yes, people are very excited, and therefore that we can definitely explore many of the tools. It's more like, that we're all kids, very curious and very excited into this playground and wonderland. And we want to try different type of things. And that right now we're seeing different observations and draw different type of conclusions, but it could be just because of the data sets that we're using. And I think, again, coming back to my points and also Pierre's point is that it's better that let's start building this better data sets before that we draw the conclusion in terms of which one is better or not.
Yeah, thanks for the talk. I had a question on causal forecasting, which I think is also very important.
Yeah.
But for, if we talk about data scarcity, as you did right now, being a problem for causal forecasting, that is a huge problem, right? Because we don't observe the counterfactual. So what's your opinion on, will we ever be able to, how do we get around this data scarcity, especially in light of foundation models?
Yeah, I think that's also a very good question. My research in time series started with causal analysis using Granger causality. I think that I was, the only people in machine learning community utilizing the Granger causality and would quite challenge a lot for the approaches. But at the same time, I think that this is one of the fundamental questions in terms of time series modeling. And I totally agree that the challenge is not only because of the causal modeling technique, but also because of the limited amount of data. And the way that we think that we get around this, or at least that there are some potential promises, is that we have built this foundation model. So that means that there is some generalization capabilities. either utilizing this transformer-based architecture or utilizing this deep generative model. One of the main trends in machine learning community right now is that we want to see how we can utilize the simulation data to compensate for the limited amount of observation data. And this is one of the major challenges in many applications we work with, either in climate or earth science. You know, when we work on earthquake prediction, there's very limited number of data, and we don't want to see a lot of data anyway. And there that we really want to compensate the limited observations with simulation data. And that is one of the approaches people have been working on and developing. And then when we talk about building the simulations, then there are two approaches. One is this data-driven approaches, and then there's also the simulation-based approaches where they incorporate all the different type of physics principles. So by utilizing either approaches or hopefully combining the two, we think there might be some possibilities to get around this data issue. And then there is secondary inputs where we also want to get access to. That is something I didn't have time to talk about, is really utilizing the domain knowledge and getting access to a lot of these physics principles, because they are only giving us some causal relationships that is really partial of them. But we were hoping that by utilizing this partial causal relationship, we'll be able to utilize also, additional data so that we can reconstruct more of the causal structures. So it's definitely a very difficult question and very important, and there are many research ongoing, definitely. Yeah.
Jade, we have time. Last question.
Yeah, thanks for your amazing talk. I have a short question. Do you think there is an issue of information leakage in LLM prediction? I mean that, the training data set of LLM is very, very huge. So maybe it actually includes the test part of our forecasting task. Yeah.
Yeah, that's again, this really touches something that's very dear to my heart because I participated in many different type of data mining competitions or machine learning competitions. So one of the competition we win is this KDD 2019. This is on breast cancer forecasting. And the way we win it is by actually identifying the leaking information, that is the patient ID, that is actually the most distinguishing feature. And this is because the way the organizer constructing the data set is getting the data from one hospital, that is cancer hospital, and also other hospital from typical hospital. And then they just, I think they're just like a little bit careful, not very careful manipulation of generating the patient ID that reviews that type of information. So we also later have a paper on how to control the information leak in the paper. I don't think this is really something the community discussed very much, especially when working carefully on the time series forecasting. And I think that this can be a potential issue, but at least for the data sets or the results we showed, we try to be really careful about preventing the information leak, so that we conduct experiments in a careful way to not including additional information. But I think that whenever we utilizing the system, for example, in finance system or in supply chain management or many transportation system, these are all real-time application, and they will basically give us the verification. So hopefully this will prevent us from, the information leak risks in there. Yeah.
Thank you. Thank you.
Thank you very much, Lanyu. I think we should thank Yanyu again for the great talk.
Thank you.